Muy buenas tardes a todas y a todos. La verdad es que es un gusto poder organizar esta serie de webinarios sobre tecnologías y autismo en el Orange Digital Center. Hoy tenemos la suerte de contar con el doctor Matthew Goodwin, catedrático de la Universidad de Northeastern en Boston, en Massachusetts, en Estados Unidos. Es una persona a la que tengo una gran admiración profesional. Sigo sus trabajos desde hace muchísimos años y siempre me ha llamado la atención su capacidad de preocuparse por las personas que tienen mayores dificultades. Dentro del espectro del autismo hemos podido ver muchísimos progresos en las últimas décadas, pero siempre hay algunos perfiles, como los perfiles de los que nos va a hablar hoy Matthew, que resulta más difícil encontrar apoyos para ellos, ¿no? Hablamos, por ejemplo, de personas jóvenes autistas que por diferentes motivos han tenido que pasar una temporada ingresadas en unidades psiquiátricas hospitalarias y que son situaciones muy complejas que cuando conocemos estos casos muchas veces no tenemos una respuesta para ellas, ¿no? Creemos que es muy necesaria la investigación en este ámbito y en el caso de, pues bueno, Matthew Goodwin pues lleva trabajando en el uso de tecnologías innovadoras para la mejora de la calidad de vida de las personas autistas que mayores dificultades presentan desde hace ya muchos años, por lo menos desde principios de los años 2000, que conocemos sus estudios. Y bueno, pues él hoy nos va a hablar de un estudio que han hecho muy interesante, muy, yo creo que rompedor, en el que, pues, bueno, han utilizado tecnologías de inteligencia artificial y biosensores portátiles para detectar las conductas lesivas en jóvenes autistas con unos minutos de antelación a que aparezcan. Esto no solamente es un hallazgo muy importante a nivel científico, sino que, pues bueno, leyendo las investigaciones que han ido publicando sobre este ámbito, vemos que han ido aprendiendo mucho sobre cuáles son los factores que pueden llevar a este tipo de conductas en estas personas y que nos arroja mucha luz para tratar de comprender un poquito más eh, qué es lo que puede estar ocurriendo y sobre todo pues contar con más recursos para poder dar algún tipo de apoyo cuando esto ocurre. Así que nada, muchísimas gracias, Matthew. Cuando quieras puedes empezar.
Thank you very much. Everybody can hear me okay? Okay. It's a pleasure to be here. Thank you for this invitation. I direct the Computational Behavioral Science Lab at Northeastern. This is the mission of the lab. I joke sometimes that our team is like X-Men Academy. We're coming from many different disciplines, some in affective science, in behavioral science, psychology, and computer science. And my interest is looking at the boundaries of these disciplines for the purposes of better understanding, supporting, and evaluating human development. I've been in the field of autism now for about 30 years, and Gerardo, you're correct that the work I'm presenting today began 20 years ago. And with advances in commercially available biosensors, machine learning techniques, data visualization, signal processing. Now that we can access the community, we are able to obtain data and really kind of push the boundaries of the current clinical state of the art. I would imagine most people who are joining right now are aware of the fact that autism has been increasing in its prevalence quite dramatically. When I got into the field 30 years ago, it was 1 in 1,000. Today, it appears to be 1 in 36 by age 8. We do not know what is causing this rise. We do not have biomarkers that identify autism. It is behaviorally defined. If we look at the most recent Center for Disease and Control Prevention census in the US, of a rate of 1 in 36 children would suggest then 2.7% of the general population, which equates to 78 million individuals with autism worldwide. Of those 78 million diagnosed, 27%, according to the CDC, meet criteria for profound autism or individuals with high support needs. So I'll come back to that a little later and help you define kind of what that phenotype is. But I want to quickly talk about this Lancet Commission. So this was published in 2021. It was led by an international team of leading autism advocates and researchers and nonprofit foundations on the future care and clinical research in autism. And I've pulled out a few excerpts of their key messages based on their review of the prevailing literature and their conclusions and guidance. And so they concluded that of the 78 million people worldwide with autism, the majority do not receive support from or have access to adequate healthcare, education, and social services. That children and adults with autism can have happy and healthy lives, but urgent action is required to promote those outcomes. They are not going to happen on their own. Autism is heterogeneous, meaning there's a lot of individual differences and variation within the same diagnostic label, and it requires personalized, evidence-based assessments and interventions that are accessible and affordable to every person that can improve the lives of individuals and their families. That a stepped care and personalized health approach to delivering services and monitoring effectiveness across time provides a framework for efficient and equitable distribution of resources to improve outcomes. And finally, research that will result in immediate improvements in the lives of people with autism and their families should be prioritized. And I want to underscore that these issues are particularly important for those on the autism spectrum who are non-white, who experience lower social economic status, who live in rural settings, and who have higher support needs. All of those attributes preclude participation in research and then the benefits thereof. So again, panning out a little bit bigger picture before I'm sort of trying to establish the context and the motivation for the work. I, for quite a long time now, I'm a behavioral scientist. Experimental psychology is my PhD. I did a postdoc at MIT and in the media lab and was hanging out with a lot of computer scientists and electrical engineers because I was concerned with the fact that an overwhelming majority of our published research in autism occurs in laboratory settings that are strange places with strange people where you're being asked to engage in tasks that you've never done before for a vague period of time and then expected to act naturally. The overwhelming majority of the published literature on autism, if you look at the participant section and the demographics and the description of the sample, you will see that the majority of published findings are in individuals who have normal IQ, who have fluent, receptive, and expressive verbal ability, and can essentially deal with a lot of novelty and sensory input and be able to contribute data. If you're talking about individuals who have an IQ of 50 or below, who have poor expressive or receptive language, who adhere to non-functional routines, who have sensory sensitivities, that setting oftentimes makes it very difficult for them to contribute data in a laboratory-based setting. And so I got interested in learning about these subdisciplines within computer science called affective computing, and then wearable computing and ubiquitous computing. And I've kind of collapsed these into this larger label of telemetrics, which is basically defined as a sensor that can record information from a distance, be stored in a centralized server with a timestamp, and have argued that behavioral scientists could have some major advantages by adopting telemetric approaches because they can enable us to be less intrusive in our measurement, provide more longitudinal recordings that can be performed in naturalistic settings. And that if we can instrument people or we can instrument spaces, essentially take the lab to people instead of bringing people to the lab, we can reduce reactive arrangements or, I think of this a bit like the Heisenberg principle. The process of studying something changes the nature of the thing that you're observing. Bringing a stranger and following a child around, that child is probably reacting to the presence of the stranger, maybe not necessarily other input in the environment that might be driving their behavior. So if we can take the lab to them, we should be able to reduce reactivity and increase compliance, their ability to contribute data. Because these sensors are mobile, we can observe in naturalistic settings, the home, clinic, community, hospitals. That increases our ecological validity. That is to say that we're observing behavior in biology where it's happening in a naturalistic space, not a contrived artificial laboratory. These sensors can record many different signals simultaneously, which lends itself well to data visualization, which I have found is a very helpful way to generate hypotheses about how different types of data or different behavioral, physiological, environmental factors might be interacting with each other. To the extent that you know what signal you're looking for in your sensor data, machine learning algorithms now are able to run quickly enough with the kind of computational power we have access to in the cloud and through distributed phones and processors that when we see a signal, we can provide just-in-time feedback. We can take data collection, analysis, and response online. It's not gathering data, storing it, analyzing it, and then conjecturing about what you could do in the moment. And if you know how you want someone to respond when you detect a signal change in a sensor in real time, we can start to provide just-in-time adaptive interventions. So these are all affordances for me, generally speaking, about how computing sciences can impact behavioral sciences. And then I will, for the duration of the presentation, show you some applied examples of this in the context of profound autism and aggressive behavior. For those who might be attending who are interested in math or interested in research design or kind of more quantitative, I put this in because telemetric recordings provide intensive longitudinal data. They're continuously recording, oftentimes passively, not requiring conscious input on the part of the person being observed. And they're giving us very dense repeated measures over both short and long periods of time. I'm showing you an image of the Cattell data cube, really just to illustrate that there are 3 dimensions when we're collecting data. You can be at the person level, that's P, so the number of people, the greater number of people you have, the more power you have or sensitivity to detect differences. We also have X, that's the number of variables. So the greater number of dependent variables you include in an evaluation, the more likelihood that you have sensitivity to detect differences. And then what's often neglected in general behavioral science that telemetrics, I think, brings as an affordance is time and sampling over time repeatedly. And so altogether, getting these longitudinal person-dependent approaches where an individual is being evaluated over time and they serve as their own control in time. So I'm not comparing person A to person B necessarily. I'm comparing person A at time 1 to time 2 to time, up to infinity. This has some really nice affordances in that we can measure multiple things simultaneously within a person and look at the effect that maybe different cognitive, biological, behavioral processes are having within a person. So sort of internal validity and relationships across levels of measurement. We can better characterize patterns over time. So instead of just a pre and post or 3 observations, all you're ever going to be able to do is fit a line. We're not able to kind of catch the distribution that is probably going to be more like a waveform. To the extent that you are capturing proximal events and behavior closer to their occurrence, because you're having repeated measures in a continuous fashion, it does help us use temporal precedent as a foundation for causal inference. So instead of just saying 2 different variables seem to correlate, you can't really say something about cause and effect when you've only got 2 variables and 2 time points. But if you have multiple measures over repeated periods of time, and you see that one variable changes before another variable changes, and that second variable rarely changes after the first variable has occurred, you have a stronger foundation to say what is causing and what is being affected. Okay, so now we'll get into autism. So I always find it informative to return to sort of the original observations and characterization of autism. As many here probably know, both Connor in the US and Asperger in the EU around 1944 were seeing the same kinds of children. They were not communicating with each other. They were publishing in different languages, but they had strikingly similar conclusions about what differentiated autism from other childhood pediatric disorders. I'm mostly focusing on the one at the bottom that I have highlighted here, which was their observation of an anxiously obsessive behavior pattern designed to maintain sameness, limiting spontaneity, and leading to rage or panic when external conditions do not meet the individual's demands of the moment. So I'm going to transition here in this next slide, and then I want to show you a brief video. Surveys in the literature suggest that as many as 2/3 of individuals with autism engage in aggressive behavior. So this includes physical aggression to other people, self-injurious behavior, major tantrums, meltdowns, property destruction, and in some instances, elopement, getting up and sort of darting out without any notice. This class of behavior is one of the primary reasons why autistic individuals are referred to behavioral healthcare services. Aggressive behavior presents imminent safety risks for the individual engaging in that behavior and other people in the environment. Families report that aggression increases their stress, their isolation, and their financial burden, and it decreases available support options. They repeatedly make 911 calls, emergency room visits, and when things get bad, long-term psychiatric inpatient care to help manage aggression. But we have to remember that these settings are meant for acute crisis, not long-term chronic care. They're not available to everybody, and they're very costly to communities. On the other side, professional support staff report greater injuries, a higher number of insurance claims, more job turnover, and burnout when providing care to an individual who engages in repeated aggressive behavior. And aggression is especially impairing and refractory to intervention in the 30 to 40% of autistic youth who are non-speaking. Their inability to provide reliable self-reports about their distress can lead to behaviors that seem to occur without warning, out of the blue. sometimes long after an observable trigger. And I would contend that parents know their children probably better than any other service provider. And when you talk to many parents about their child's aggressive behavior, they'll say that they can't predict when it's going to occur. By the time that they're aware that there's an issue, the behavior has already happened, which puts them in really a crisis management and a respondent mode. It does not enable them to prepare or try to prevent or to de-escalate a child's arousal before the behavior has occurred. And that's essentially what I am trying to enable, is that we can anticipate and engage in preemptive interventions that may prevent these behaviors, or we can respond in a more organized way that mitigates the damage that they can do. So I'd like to play a short video that conveys better what I'm saying by someone who has lived experience. Gerardo, if you could just do me a favor, just from our pre-testing, when I started, just give me a thumbs up to ensure that you can hear the audio.
Jody is 26 years old. She is diagnosed with profound autism. She is sweet, she is affectionate, she has the purest soul, and she has serious episodes of self-injury and aggression. 27% of people who are diagnosed autism spectrum disorder meet the clinical definition of profound autism. It's defined as people who have autism who also have IQ below 50, who are nonverbal or minimally verbal, and who require 24/7 supervision in order to maintain safety. The biggest issue that families of kids with profound autism describe is really the self-injurious and aggressive behavior. There's nothing harder than watching your child hurt him or herself. Children will bang their heads against the floor with such ferocity that they experience detached retinas. They scratch, they bite. Some of these behaviors make it impossible to go out and participate in community activities. So for that reason, a lot of families stay home. They become very socially isolated. Often before these incidents take place, there's no warning to parents. There's no outward sign that you can visibly see that something is going to happen. One incident that really sticks out in my mind is when Jody was 5 years old and her sister was 3 years old. I was driving our minivan. Jody wanted to go back home, but we had to stop and do an errand. So when she saw that the car was not proceeding in the route that she knew to be towards home, she managed to unbuckle herself and came at me, started hitting me and punching me and screaming. I sort of pushed her off me. She started going after her sister. It was the most dangerous situation I think I've ever been in my life, with my 2 children in the car. It's hard for me as a mother when my child is hitting me, but it's worse when she hits my other daughter. Especially when she's helpless, strapped in a car seat. So that's when I don't really love to think about too much, but that was. That's why the biosensor research that Matthew is doing is critical. If I had some warning that Jody was about to have an aggressive outburst, I could have pulled my car over. I would have tended to her. I would have made sure that we were all safe. If we had that additional tool, I think I would be a little bit more relaxed. I wouldn't feel like I had to know everything about every environment before I took her, because I would know if the invisible stress were starting, I would be able to intervene. Most of the research that's being done in autism right now is being done on individuals who are able to get themselves to universities to participate. This type of research can be done in their own community. It can be done in their school. It can be done in their home. It's a way to bring the research into the community, as opposed to bringing people with autism to the university. These are not bad kids. They're not acting out because they're bad or they're mean. It's part of their autism. What the data from the biosensor allows an adult to do is to intervene compassionately. When someone intervenes, you're helping them to regain their control and be better able to participate in community activities. It really has huge potential to improve the lives of people with profound autism.
So traditionally, aggressive behavior in autism has been conceptualized as escape and avoiding demands, as oppositional behavior, as defiant behavior, and in some instances, forensic, meaning an individual takes pleasure in the harm that they are causing another person. An alternative conceptualization is that these behaviors are a maladaptive attempt to express or modulate physiological arousal due to distress, so homeostatic regulation. And there's emerging research that suggests that there are several factors associated with emotion dysregulation in autism that singly or in combination could lead to aggressive behavior. So if you have limited emotional language or alexithymia, difficulty identifying and articulating an emotional state, it's going to be very hard for you to convey to other people when you are feeling distress. If you have cognitive rigidity or poor flexibility, it's going to be hard to understand and adapt to changes in the environment. If you have low inhibition, it is hard to resist acting out on an impulse. If you have poor problem-solving skills and poor abstract reasoning, it's going to be difficult to think about how best to cope with a change in the environment. If you have difficulty reading social and emotional cues from other people's affect and gestures may be ambiguous and threatening to you because you don't understand what they mean. If you have sensitivity to change and environmental stimulation, things that most of us don't notice or we tune out may not be so easy for you to do, and the environment can be overwhelming. And then biological predisposition. So we have evidence that there are differences in genetics and neural circuitry and physiological arousal responses in individuals with autism. Any one of these features, and often when we talk about high support needs, many of these characteristics are present within the same child. I guess the simple way to say this is the world may be experienced in a different way by a child with autism who has some of these different attributes than how the rest of us experience, understand the world, and are able to cope with it. So the present work is working under the assumption that aggressive behavior is associated with physiological and behavioral fight or flight responses. We know that in typical youth, a greater ability to regulate physiological arousal is associated with fewer behavior problems. That studies of disorders characterized by emotional and behavioral dysregulation, like bipolar disorder, antisocial behavior, report a strong association between physiological responding and symptomology. We have prior research in autism demonstrating that an individual may engage in aggressive behavior and attempt to communicate or alleviate distress and decrease or increase arousal to achieve autonomic equilibrium. However, and it's what I'm showing in this conceptual framework, if these behaviors are punished or their underlying function is not satisfied, physiological arousal can increase, exacerbating and perpetuating an escalating loop of distress, arousal, and aggression. So I'm showing a brief schematic. I'll talk this through, so if it's hard to read, don't try to do so. This is neural circuitry in the central nervous system, our brain, and how it's connected to our peripheral nervous system out in the body. from Robert Sapolsky. He is a stress researcher, endocrinologist at Stanford University. And he's demonstrating that stress pathways are diverse and involve very different regions of the brain in feedback loops that can greatly amplify a response. So this is somewhat simplified, but if we sort of follow the arrows and the numbers, the first important thing to see is that stress is an appraisal in the frontal cortex. So what stresses me may not stress you. It's a perception about whether there's a threat in the environment, or a change that requires me to adapt my behavior. If I appraise something as being threatening or ambiguous, we get so actual or perceived threat. If our cortex is unsure, it sends a message to the amygdala. That's the kind of number 2 small. That is our novelty or threat detection center of the brain. It can also send a preconscious signal to the hippocampus. That's where arrow 3 is coming. That is our memory store for past salient events. These are 2 of the most important systems within the limbic system that are preconscious. It doesn't require conscious input to engage these circuits. If we appraise stress, the hippocampus and the amygdala say we've seen this before and it went bad, or we've not seen this before and we should be on guard. The amygdala releases corticotropin releasing hormone, which stimulates the brainstem. That activates the sympathetic nervous system via the spinal cord. I'll have a slide subsequently and walk through the sympathetic and parasympathetic nervous system. In response to that activation, the adrenal glands, which sit atop the kidney, produce the stress hormone epinephrine. And a different pathway simultaneously triggers the adrenals to release glucocorticoids. And these 2 types of hormones act on muscle, heart, and lungs to prepare the body for fight or flight. Then the recursive that you're seeing come back up, 7, if the stress becomes chronic, glucocorticoids induce the locus coeruleus and release norepinephrine that communicates with the amygdala, which produces more corticotropin releasing hormone and ongoing reactivation of stress pathways. And what's important to remember about that last connection is that chronic activation of this stress cycle can become neurotoxic and kill cells that make the hippocampus and the amygdala less able to discern perceived from true threat to safety. Once we are out into the peripheral nervous system, you may recall that we have 2 primary divisions, the sympathetic and the parasympathetic. The sympathetic division is stimulating, fight, freeze, and flight. The parasympathetic division is inhibitory, and that's about rest, digest, and recovery. You could think about this metaphorically as the sympathetic nervous system is the accelerator in a car, and the parasympathetic is a brake. For all incoming input, our central nervous system and its appraisals and the peripheral nervous system are working dynamically, the sympathetic and the parasympathetic, to achieve autonomic equilibrium. And if you look at the bodily organs, each division of the sympathetic nervous system is innervating, with the exception of the skin. The skin is only sympathetically mediated. All the rest control these organs. So when there's high sympathetic tone activation, we get pupillary dilation, which helps us take in more visual information. We get increased breathing rate, which gets more blood into our oxygen stream. We get glucose stimulation for faster burning energy. Our heart beats faster to pump bloods to major muscle areas. Our blood vessels constrict and move away from the surface of the skin in case we're to get cut or bitten. It's going to reduce salivation. It's going to inhibit digestion. It's going to inhibit reproductive function because those are all luxury metabolic demand that are not needed in the moment for survival. After a stressor has passed, you have avoided it or you have coped with it or you've been removed from the situation, the parasympathetic nervous system is going to kick in and it's going to basically do the converse of everything I just mentioned to you. The one thing I forgot to mention that I should have is in increased sympathetic tone, we also get increased sweating, which is trying to cool the body down. And some have theorized that it makes us our skin surface more slippery, easier to evade. So after the stressor is passed, then the parasympathetic is going to come in. It's going to contract the pupils, stimulate salivation. It's going to slow breathing, slow heart rate. It's going to stimulate digestion. It's going to basically have the body start to try to repair for any damage that was done when you were in an extreme stress state. Okay, so now you should have most of the background and context for these hypotheses and objectives and the evidence that we have obtained to date. So our hypothesis is that physiological arousal precedes aggressive behavior. The three target behaviors that we are focusing on in this work is aggression to other people, self-injury, and major tantrums and meltdowns. Our objective is to test whether the proximal onset of aggressive behavior can be predicted from preceding physiological signals using wearable biosensors and machine learning algorithms. A little bit about the data set. So this is the autism inpatient collection. This is where we recruited our participants and we deployed technology and collected data. This is sponsored by the Simons Foundation Autism Research Initiative. Safari Autism Inpatient Collection began in 2013, and it includes 7 psychiatric hospitals and clinics throughout North America. Their goal is to recruit 1,600 autistic youth who have higher support needs and share de-identified data, including genetic sequencing, with approved researchers. Inpatients with autism are underrepresented in modern large data repositories. And it's a high throughput unique setting to efficiently collect large amounts of standardized data and improve understanding of this understudied segment of the autism population. While data collection primarily focuses on phenotypic and genetic data, the inpatient setting is a good platform to identify mechanisms underlying emotional and behavioral symptoms that could inform intervention. And we felt it was a unique ability to study aggressive behaviors in natural environments due to the safety of the inpatient environment and control over environmental factors. So it's staffed 24/7. When people are engaging in these behaviors, there's somebody to respond and keep that child safe. So of these 7 sites, we were successful in recruiting 4. That's Spring Harbor Hospital in Portland, Maine, Bradley Hospital in Providence, Rhode Island, the Western Psychiatric Institute in Pittsburgh, Pennsylvania, and then Cincinnati Children's Hospital Medical Center in Ohio. We had consent from 86 families, and we were able to collect data from 70 individuals across these 4 sites. Of the 16 individuals who did not contribute data, half of them, 8, were discharged before an observation could be made. The other half wouldn't tolerate wearing the biosensor. But 70 of the 78 tried could comply. So the sample is between 9 and 15 years old. They're predominantly white, they're predominantly male. More than half are minimally verbal or non-speaking, and more than half have an IQ in the moderately to significantly below average range. The length of hospital stay for the 70 individuals across the 4 sites ranged from 8 to 201 days. The biosensor that we deployed, and this is what the inpatients are wearing, is a wrist-worn device by Empatica. It's called the E4. It is shockproof and waterproof. It records and streams data live. It records blood volume pulse using photoplasmography, where changes in blood oxygen are measured to calculate heart rate and heart rate variability. Heart rate variability being distance timing between beats. Heart rate is how forcefully the heart is beating over unit time. It records electrodermal activity or skin conductance, which is a measure of sympathetic nervous system arousal. It records body surface temperature through what's called thermopile, and then it records 3-axis acceleration, which is capturing movement and physical activity in a 3-dimensional space. We also created a custom mobile phone application where we had operationally defined, which you can read on the slide, aggressions to other people, aggression to self, and then major tantrums. And so so the children are wearing the biosensor. The research staff, not the clinicians who are responsible for responding to the children, are opportunistically annotating when they observe naturally emitted aggression to self, other, or tantrums. Because of the inpatient setting, we can't record video. So the research assistants' behavioral annotations, the topography, is it an aggression, an SIB, an ED, and toggling, when did it start and an end, become our ground truth for when the behaviors are occurring. This becomes important because these are the labels that will be used for training and testing machine learning algorithms. For 20% of the data that we collected, sessions were dual recorded by an independent rater, so 2 RAs, not talking about what they're saying, independently coding. And we saw over 80% inter-rater observer agreement for each of the 3 target behaviors. So across this study duration, which was about a year, we collected 429 data collection sessions for 497 hours of data, with a median of 5 observational sessions lasting 4 hours each, or 20 hours per participant. Within that corpus, we observed 619 aggressive episodes, 2,063 tantrums, and 3,983 self-injurious behaviors, for a total of 6,665 aggressive behaviors with accompanying biosensor data that's available for machine learning. I feel bad for the interpreter right now. There are a lot of acronyms. I'll try to briefly explain what they are here. So area under the receiving operating characteristic, or AUROC, is the diagnostic ability of a binary classifier to discriminate a threshold at different levels. So that becomes our performance metric. An AUC of 0.5 and below is chance. From 0.5 to 1, so if you have an AUC of 1, you have perfect discrimination or predictive validity. Anything between 0.5 and 0.1 is sort of beyond chance. So we then have different methods. These are 3 different classes of machine learning classifiers. Logistic regression, LR, is a statistical model used for binary classification tasks. So it calculates the probability of an instance belonging to a certain class. So in this case, it's going to be aggressive behavior versus non-aggressive behavior. SVM, or support vector machines. So these are trying to find a hyperplane that maximally separates 2 different classes. So what features discriminate aggression from non-aggression after you can separate them? And then neural networks, or NN, these are capable of learning complex patterns and relationships in data. So after we balance the data, right, because there are more instances of non-aggression than aggression, so you have to equate their occurrence, we use 15-second sliding windows to extract features from the biosensor time series preceding the target behaviors. And then we're assessing logistic regression, support vector machine, and neural networks to determine how far into the future and at what level of success you can predict a behavioral aggressive onset with preceding data from the past. And we do that in 2 different configurations with 3 different cross-validation methods. We have person-dependent models, that's the PDM, and there you're basically building a classifier for each individual, and you're using sessions over time. What you'll see is SS, those are session splits. So you're training on an early session and you're testing on a later session with new data within an individual as their own control over time. And then we have population models, that's the PM, where you're training on everybody, but you're leaving one person out. And you're shuffling through all those configurations where you're now training on everybody but one, and then you're testing on the one who was the holdout. And what you can see from here, looking at the person-dependent and the population models, when you leave subjects, you leave sessions out, and you leave individuals out, all 3 classifiers are performing above chance. And some of these are performing up to 0.85 AUC. We also see that population models typically outperformed person-dependent models. And we saw similar performance predicting individual classes of behavior, the self-injury, the aggression, the meltdowns, as we do if you combine all of those behaviors and you treat them as a single class. So we're getting good discrimination, not just of when the behavior occurs, but which one is being predicted by the classifiers. In this chart, I'm showing you intensity. So we used the accelerometry data as a proxy for how vigorously is someone engaging in an aggression to another person or a self-injury or a tantrum. And we did cluster analysis on that acceleration data and basically categorized behavior labels as low intensity, middle or moderate intensity, and high intensity. And what you see across the classifiers according to AUC is essentially a dose response performance curve. So we're predicting, we're doing good job identifying high intensity and moderate intensity. It does less of a good job predicting low intensity. But when we talk to clinicians, this is acceptable performance because it's the high and the moderate intensity that are most clinical concern. The brief and not very vigorous, say SIB, can still be socially stigmatizing and problematic, but it's not likely producing the kind of physical harm that a more intense aggressive behavior is. So for the longest prediction time into the future, which we found to be 3 minutes, the best performance was achieved by support vector machines with 0.85 AUC. And we bootstrap all the data so we can generate confidence intervals. The confidence interval range for SUV or SVM was lower bound 0.84 and higher bound 0.86. Next was logistic regression at 0.80 with a confidence interval of 0.79 to 0.81, and then neural nets were 0.78. We then looked across individual sessions, that's panel A at the top, and then sessions grouped, panel B, and we observed 80% average test-retest reliability of that logistic regression model performance over time. So you can think of this a little bit as sort of stability or how well the classifier performs across repeated sessions of data within individuals. So it's robust, stable. The classifier continues, doesn't need retraining across multiple sessions. It's performing as well initially as it does subsequent. And then finally, we use domain adaptation techniques. So you're starting with the general classifier, and then you're updating that classifier, its features, as new information comes in from a new individual. And here we observed a notable increase in the population performance model when data from individuals were enriching it. And so panel A on the left is showing you with 3 minutes of prior data, we can make a prediction 1 minute into the future using domain adaptation that gives us a 14% improvement in AUC. And in panel B, or on the right, this is now 3 minutes of data from the past, making a prediction 3 minutes into the future where the population model is updated with individual data. We observe a average improvement of 6% AUC. So it's just about a year now that we published these results in the Journal of the American Medical Association Network Open. I'm sharing some of these metrics not to brag, but really more to demonstrate how interested the scientific community is in this issue and these methods. Since the time that this was published, this isn't even the most current alt metric, but it's been downloaded, the paper, over 9,000 times. It is in the top 5% of uptake of the 26,619,752 publications that they've been tracking, and puts it in the 98th percentile of what they call an attention score. So in this publication, we also added a pretty lengthy supplement that fully discloses and describes all of our methods and all of our steps in performing the analysis that generated the results that I shared with you. And then thanks to the Simons Foundation, they agreed to host the de-identified behavior annotation labels and the raw biosensor data. And I've released this now to the scientific community. So for non-commercial purposes and research purposes, somebody should be able to read the paper, download the data set, follow our methods, and reproduce our findings, and then call to arms. You know, there are people who are probably not thinking about autism and aggression, but who have background training in engineering or econometrics or physics, who deal with complex non-stationary time series and feature discovery and prediction. I would love for them to apply their more advanced modeling methods to this data. This is very hard data to access, so I'll share that effort in exchange for, if they can make a longer prediction into the future at a higher percent accuracy and share their method, we could potentially get solutions to families faster. So the current state of the work and future directions, and then I will be wrapping up and welcome any kind of questions, are kind of 3 different areas. We're working on more advanced analytics. So using transfer learning and domain adaptation to individualize models using partially or wholly unlabeled data just based on the biosensor data and the sequence of aggressions observed. We're looking at hierarchical Markov modulated point processes to account for the non-stationarity in the signals and feature statistics. We're looking at feature importance weightings. So what the supplement of the paper describes several different experiments that are configured with how much data you're feeding the classifier, how many instances the behavior occurred, and what was the level of prediction accuracy. But it's interesting. I mean, we know that if you take the biosensor data out of the model, you don't get the same predictive performance if you're just looking at the behavioral events. So that is telling us that the physiological data is providing unique variance that's enabling these classifiers to detect correctly the onset of these behaviors. And that's then leading us into a functional data analysis of the raw biosensor data. What features of the blood volume pulse, of the electrodromal activity, of the motor activity are helping a classifier correctly distinguish whether an event's going to happen or not. I also have a current grant with the Marcus Autism Center in their severe behavior unit at Emory University, who are deploying the biosensors within functional analysis of behavior. So in that arena, they are changing the environmental demands, whether a person's alone or with another person, whether it's a high sensory environment or a low sensory environment, whether you're taking away a preferred object or you're asking somebody to engage in a learned or an unlearned task. They're basically trying to elicit the behaviors across these different scenarios to determine whether these aggressive behaviors are socially mediated, i.e., they're designed to get other people to react to you differently, or whether they're automatically maintained. They're doing it for some internal regulatory function that's not dependent on another person. The distinction between socially mediated and automatically maintained has very different intervention implications about how one would support and personalize an intervention. And we're interested in seeing if we can incorporate that knowledge into our classifiers. We're also able to take video in this setting. And so we now have biosensor data in addition to video records, and now can start doing some work that combines computer vision, automated detection of the scene and the context that we can interrogate against the biosensor data. And then on the right side, we are building out a software infrastructure that enables us to take the data that's being recorded by the biosensor, stream it live to the phone where the behavior annotations are taking place, time synchronize them, push them to the cloud, run our machine learning classifiers in real time, and then push back notifications. And the idea here is that if we could develop a real-time aggression prediction and display a risk alert, that we could ask caregivers and clinicians to monitor these alerts and initiate just-in-time adaptive de-escalation or emotion regulation interventions before aggressions begin. And then we could assess the effectiveness of these alerts facilitating those preemptive interventions and demonstrate that they reduce the frequency, intensity, duration of aggressive behaviors. So I think if I were to kind of try to sum this up, I don't think these behaviors are happening out of the blue phenomenologically. That's how we observe them. But the body has to engage in preparatory changes in order to engage in these large externalized behaviors. 3 minutes of notice is enough time to do something. And if we can start pairing this technology with functional behavior analysts and interventionists, we might be able to couple clinical knowledge about behavior management plans that when you alert a parent, you have 3 minutes until this child may engage in a behavior. Stop what you're doing, take a deep breath, get organized, review your plan, and then initiate these interventions. Before they occur, we think is going to have a greater impact of harm reduction than crisis management after the fact. As several people use a system like this, we can start to learn, are there common triggers that change physiology that precede behavior? And it might not be immediate in the environment. I mean, it could be previous night's sleep. It could be seizure activity. It could be gastrointestinal pain. It could be rumination on a previous event. It could be changes in medication status. And then on the other side, as we, these systems, by virtue of how they function, are data collection devices. So as we start to learn, how did you intervene and how effective was it, based on different interventions prescribed by a supervising clinician, we might be able to start data mining what are common triggers and what are more efficacious interventions that could deliver policy-oriented interventions for new users of the system. So as you use it more, it gets better, and as more people use it, you might be able to find mitigation solutions more quickly. So I want to thank all of you for the invitation, your attention, the families and the study participants, Allison Singer for sharing her and Jody's story, my students, staff, and faculty at Northeastern, across the College of Health Science and Computer Science and College of Engineering, clinical collaborators in the Autism Inpatient Collection at the Marcus Center at Emory University, and then the funders who have been supporting this research includes the Nancy O'Leary Marks Family Foundation, the Simons Foundation, the National Institute on Deafness and Other Communication Disorders, the National Cancer Institute, the National Library of Medicine, the National Science Foundation, and the Department of Defense. Thank you. I'm happy to take questions.
Muchas gracias, Matthew. La verdad que muy interesante todo lo que nos has contado. Como decíamos al principio, tenemos ahora un espacio para preguntas. Si alguien desea abrir el micrófono, que nos lo indique en el chat y se lo abrimos desde aquí. Pregunta, por ejemplo, Marta, si estos dispositivos estarán disponibles. Entiendo que te refieres también al software, porque el dispositivo es un dispositivo que se vende, ¿no? Si los dispositivos estarán disponibles en algún momento fuera del estudio para utilizar con sus niños.
It's an excellent question. It's the one I dread every time I give this presentation. The device was not built for this purpose. It is a general consumer device that records these biometric signals. The formulation of the data and the machine learning and the push notification is not supported by the company that makes the biosensor. That is the work that we are developing. I do have every intention to try to make those classifiers and algorithms available to the scientific and clinical community. And some of the work that we're currently doing is taking commercially available sensors. So Apple Watches, Garmin watches, Fitbits, Whoops, I mean, there's many of them, Pixel watches, Samsung devices that have software development kits and APIs available. And I want to replicate some of the studies that we've done with the E4 and see if we can get similar results with them. If we are successful in that, the next step for me would be to do a randomized trial where we push notification or we suppress notification and see if there's an observable change of just knowing that it's going to happen, but not prescribing an intervention, but not being caught off guard. My hypothesis is that we will see a reduction in behavior intensity or duration if someone gets a preemptive alert. If that is in fact the case, then the next thing I would want to look at is if a supervising clinician provides guidance on what to do when you get the alert, given how much time you have and what they know about the child, can they reduce the onset, impact, duration, and intensity of those behaviors? If those next three stages all go positively in the way that I hope that they will, I think we will have an evidence base that we can start thinking about translating this into products and services. So the time scale for that is hard for me to say. I've been working on this for 20 years. I'm impatient now. We know how to do it. We know it works. There are people who want to be involved. 70 people and 7,000 behaviors is a lot, but that doesn't represent all 21 or 78 million people. So we still need more data. I know I'm talking around the answer that you want to hear. I want to see this get commercialized so it's available, but I want to be very sure that we have evidence to support the claims about it before we ask people to spend money and get their hope up before there's any commercialization. So I want it to go fast. I'm going to estimate 3 to 5 years. I would love it if it's sooner than that. But I'd say I'll keep you posted as we make progress.
Muy bien, dice Marta que sí, que ha respondido a su pregunta, que muchas gracias. Mientras surge alguna otra pregunta, yo te pregunto, Matthew, por cómo ha sido el estudio, ¿no? La calidad de los datos recogidos por el E4. ¿Ha sido siempre suficiente? ¿Habéis tenido problemas? ¿Y cómo también crees que puede ser esto que comentabas, ¿no? De trasladarlo a otros dispositivos de menor coste, ¿no? Tipo Fitbit o cosas así, que puedan ser, digamos, más asequibles económicamente. ¿Cómo crees que puede ser también la calidad de los datos al hacer esa transición a un dispositivo de menor coste, ¿no?
Yeah, good question. So there are a couple ways I can answer this. So part of the reason why I used the E4 in the first place, um, the company was a spin out of the lab I worked in at MIT who built the predicate device. So I knew how it operated and all the people who were maintaining it. They're one of the few devices that has been scientifically benchmarked against wired systems. And they give you access to the raw data and they don't do any pre-processing. So from a scientific standpoint, I have complete control over how the data is being manipulated before we're using it in a classifier. What maybe not everybody here on this call is aware of is the consumer wearables like the Fitbit and the Apple Watch and etc. They market as health, but they are licensed as entertainment and lifestyle, which means they do not have to share raw data. They do not have to disclose their pre-processing methods, and they do not have to show that their device has a level of accuracy with a medical grade device. So that's why we use the E4. But now that many of these manufacturers are letting people have software development kits, we can access that data and we can start to do those experiments ourselves. If the sensor is worn correctly across these different commercial devices, I should think that we're going to find replication of the results. It's very interesting to think about, like, what is it about the biosensor data that the classifier is learning is predictive of the event? Is it level change, slope change, variability over time, increased noise in the data? I don't know if it's signal or noise that's helping it discriminate. In some ways, it doesn't. I mean, scientifically, I want to know. In some ways, it doesn't matter if it's reliable and always produces the same utility. Like, we all drive cars. None of us really know how they work. But every day you put the key in, you got gas in it, and you've got a battery that's charged, and you turn it, it works. So I don't know. That's a to be determined, and we'll share that as we find it. There are limitations, though, even to those devices. If they're not charged, or you're not wearing it, or you take it off, you don't have any of the other affordances. And so we're also tracking developments in adhesive electronics, temporary tattoos. I suppose at some point we're going to have subcutaneous and swallowables. I'm a little nervous about those, but there are advancements being made where you could put a temporary tattoo on the site of location with electronics that are embedded that have very low power requirements. You can't take them off and you get continuous streams of data. I think ultimately that's going to be a better form factor than a device that you can take off and lose.
Ah, muy bien. No sé si tenemos alguna otra pregunta por ahí. ¿Cómo ha sido? Ha habido dentro de, bueno, porque este vídeo que nos has enseñado, ¿no? Sale una madre explicando un poco la situación, pero ha habido, ¿cómo habéis gestionado con las familias, ¿no? En el estudio, porque con 70 familias entiendo que habrá sido pues muy variable en diferentes sitios, ¿no? A la vez que lo habéis hecho. Eh, ¿Cuál ha sido la experiencia de las familias y de las propias personas autistas en la medida en la que ellas se hayan podido expresar?
Yeah, good question. So, it was all in the same setting. I mean, there's four of them, but this is all hospital inpatient, and they're there between 8 and 200 days. So I think about a couple things. I mean, we had a very high study enrollment rate given the number of families that we asked. So, remember too that these are general hospital flow. So people aren't living there all the time. It's based on how they're using that clinical service. So as somebody gets admitted to the psychiatric unit, they're then getting a description of the study and asked if they want to consent. And so we don't really have control over people, more people coming in or the rate that they're coming in, nor do we have any control over how long they're there and when they get discharged. But we had high sign up, and then 70 tolerated wearing the device, only 8 did not. So that tells me that if you introduce this technology and you desensitize and you model wear, once they're wearing it appropriately, they'll leave it on. We had 5 on average sessions lasting 4 hours per person. Some of those were many more sessions. So that's also telling me that they'll continue to wear this device over long periods of time. And the families that we spoke to basically said, if you can do anything better than guessing when it's going to happen, this would have incredibly high clinical significance. So I take this all to mean that it's feasible, it's addressing a gap, and it could have clinical implications. Now the question is going to be going forward, how well can we reproduce these findings with different devices in different settings? So some of those settings would be outpatient clinics, would be specialized autism schools, would be typically developing schools where there are maybe autistic learners who are integrated. And then, really the frontier would be in the home environment. And so I would like to systematically reproduce and test with different devices across each of those different settings. And then I think we'll learn who is it good for, when, on which environment, whether it's always 3 minutes and 80%, it could vary. It might be more time, less time, higher or lower accuracy, depending on the sensor and the setting.
Muy bien. Pues muchísimas gracias, Matthew. La verdad que ha sido un placer escucharte. Gracias también a Sergio por la interpretación, excelente como siempre. Gracias, Lupe. Gracias a todas las personas que nos habéis acompañado esta tarde. Bueno, seguiremos con otros webinarios que os iremos anunciando próximamente. Y bueno, hasta la próxima. Gracias.
Thank you very much. Bye all.